Electrostatics, Electric Scalar Potential. It is on Electromagnetic Field Theory, lecture number 1.30. Electric scalar potential is considered an important property or characteristic of electric fields. It is able to provide some critical and important information pertaining to the nature of electric fields. In the present session, we consider first the definition of scalar potential in the field. Then we go to derive expressions for potentials in the fields due to various source distributions. Like first we consider discrete charge distributions, and then we go to continuous charge distributions. Electric scalar potential, like field intensity, displacement density, is one of the parameters, quantities useful to give an insight. It is able to provide certain critical information regarding the nature of fields. It has some advantage when compared to field intensity and displacement density. That is, it is a scalar function and hence easy to deal with when compared to vector functions. It is a function of source distribution. What he says is, it depends upon shape and size of the source distribution. It is also related to field intensity. In fact, it is defined with respect to field intensity surrounding the source charge distribution. Potential function obeys superposition principle. It is continuous in the field and also single valued at any point. Here in this slide, important point is, if you consider some charge distribution, surrounding this charge distribution, field exists. If this charge distribution is stationary, this is electrostatic field. If you consider a point in the field, at this point there exists certain field intensity. At this point one can define potential also. Field intensity is function of charge distribution. In the same way, potential is also function of charge distribution. This is one aspect. Another aspect is E and V both are sourced by one charge distribution. Parents are same. Therefore, there must be some relation between E and V. He says V is related to E2. It is a function of source distribution. This is one aspect. It is related to field intensity also. This relation is because both are arising from the same source. Here a definition of potential is given. Consider an electric field surrounding an arbitrary charge distribution. This is arbitrary charge distribution. When I say arbitrary, it may be a point charge, it may be a group of point charges, it may be a line charge, it may be surface charge, it may be volume charge, or it may be a combination of one or many of these charge distributions. So some arbitrary charge distribution is there. Surrounding this distribution, field exists. Everywhere field is there. Now, the scalar potential, actually this is called absolute potential. Another potential is also there, relative potential. Here, definition is absolute potential, regarding absolute potential. The scalar absolute potential denoted by V at an arbitrary point P, here is point P, arbitrary point P, in the electric field E is defined as work done by any external agency other than field to bring unit positive charge from infinity to the point under consideration. He says potential here is work done by an external agency to bring a unit positive charge from infinity. Let us say this is infinity. Here plus 1 coulomb, you consider plus 1 coulomb. To move plus 1 coulomb from infinity, this is infinity, to point under consideration, you have to perform certain amount of work. That work is potential. As the potential is work done per unit charge, its units are joules per coulomb, usually called volts. It is indicated by capital V. Mathematically, one can write Vp is equal to minus infinity to point P E dot dl. How this expression has come from the definition, defining a word statement. For to understand that aspect, explanation is given. A point charge in field experiences Coulomb force. See, here is some charge distribution. Charge distribution is there. Now let us say there is a point charge here. Coulomb says this charge, let us call it test charge. It experiences force, and this force is given by, let us call it small q, this charge. Q multiplied by E, electric field intensity. This is your Coulomb's law. If both are positive charges, the force is repulsion. Therefore, the field tries to move small q away from the source charge. Now, let us suppose I want this charge to be here. Let us suppose here is a point P. I want this charge, small q, at P. Then what is to be done? I have to push. Somebody has to push this charge towards P. Pushing means moving and also applying force. So you are performing certain amount of work. How much work you have to perform? Work is given by F into distance or F dot dl, initial point and final point. See, this is the work expression for work. Now, force we have to apply is the force that is required to counter the Coulomb force that is experienced by small q. Coulomb force is given by Q into E. So the force which you have to apply requires to be countered or against the Coulomb force. Therefore, the force you have to apply is minus F. This is the force one has to apply. This is one aspect. Minus QE is the force you have to apply. This is one aspect. Another aspect is the definition of potential is force required to be applied on a unit positive charge. So Q is +1. Therefore, what happens is the force you have to apply is minus E. Now substitute minus E in place of F. Therefore, what happens is potential becomes initial point, final point minus E dot dl. And here initial point is the point where you are starting, that is infinity. Therefore, initial point is or initial limit is infinity. That way, this expression has come into being. Same thing is being told in the explanation of a point charge in field experiences Coulomb's force. Work done in moving these charges, dot product between force and distance. Force is equal to field intensity when charge is unit positive charge. Hence, integral E dot gives work done. Negative sign is to signify work is by external agency. Lower and upper limits are initial and final positions. Initial position of the charge is at infinity. So, lower limit on the integral is infinity. Lower limit at infinity is acceptable in all cases, except when source charge distribution itself extends to infinity, like infinite straight line or infinite sheet charge. This definition is okay for most of the cases. This is not valid for all charge distributions. What he is trying to tell in the last para is, for most of the cases, this is the definition, acceptable. We can work with it. But when the source distribution itself extends to infinity, then this is not useful. And if you try to calculate potential using this expression, in such cases, then you will land in trouble because integration has to be performed. It may result in an indeterminate value. Now the definition there is B minus integral E dot dl is its integral relation. This integral relation can be converted into a differential relation. It is E equal to minus grad V. How this relation has come into picture, how one is able to convert integral relation into this differential relation? The answer is dV. See, from the defining integral relation, dV equal to minus E dot dl. Okay, but from integral calculus, dV is dou V by dou x dx, dou V by dou y dy, dou V by dou z dz, and this can be written as dot product of two quantities, dou V by dou x cap, dou V by dou y cap, dou V by dou z cap. This side dx x cap, dy y cap, dz z cap, plus sign are there in both cases. This is, we know this is grad V, whereas this is differential length in Cartesian system. By comparing the defining differential relation by comparison, defining the relation can be obtained by comparison. See, dV is grad V dot dl. dV is E dot dl. Now compare. E becomes minus grad V. From the defining differential relation of potential, the curl of field can be found. Curl, what is del cross E? It has been told by one gentleman by name Helmholtz, who says that fields are completely definable or definable completely by two aspects. Two of their aspects. What are the? One is curl, another is divergence. So curl and divergence are quite important parameters, aspects pertaining to fields, because they give complete information, total information. There is nothing there that is not given by these two. Now curl of E. What is curl of E? Curl of E is E. In place of E, I can substitute grad V. When you substitute grad v, what happens? It becomes 0 because curl grad v is always 0. This is vector identity. Hence, we can conclude field intensity grad v equality. Field intensity is minus grad v. This equality implies curl of electrostatic field is 0. Here I want to mention one fact. This is so for static fields. Later we come across dynamic fields. In case of dynamic fields, del cross E is not 0. When curl is 0, the field is said to be irrotational. Let us suppose there is a field, its curl is 0. It is called irrotational field. From Stokes' theorem, 0 curl implies closed line integral of field is 0. So del cross E 0 implies closed line integral E dot dl is 0. Both means the same. This is differential relation, this is integral relation. In an electromagnetic field theory, we come across two relations: integral relation, differential relation. Okay, del cross E 0 is differential relation, whereas E dot dl closed line integral is integral relation. When line integral of field around any closed path is 0, the field is said to be conservative. So irrotational, conservative, these are properties of electrostatic fields. It implies energy of the charge field system remains constant during charge motion in the field. Hence, electrostatic fields are irrotational and also conservative. There are two types of potentials. One is absolute potential, another is relative potential. What is absolute potential? Absolute potential is one which is computed with respect to zero potential reference point. For finite charge distributions, zero potential point exists at infinity, and hence infinity is used as lower limit on the defining integral of potential. For infinite straight line charge, zero potential point exists nowhere. It exists not, and hence absolute potential exists not. So as far as infinite straight line charge is concerned, absolute potential, it doesn't exist. For infinite plane sheet charge, zero potential point exists at the origin, and hence reference to find absolute potential is the origin. In such case, lower limit has to be, it is required to be 0 origin. For all other distributions, except of course finite straight line one, lower limit is infinity. Relative potential is one computed with respect to a point where potential is finite and non-zero. Mathematically, VAB means potential at point A with respect to B. It is minus B to A E dot dl, which is of course VA. VA means absolute potential of point A, absolute potential of point B. VA is absolute potential at A, next one is absolute potential at B. So what exactly is this relative potential? See, you consider some charge distribution. Absolute potential is the work required to be done to bring a unit positive charge from infinity to the point P under consideration. This is P, this is infinity. You need to do certain work. That work is absolute potential. Of course, here the charge is unit positive charge. Charge that is moved from infinity to point is unit positive charge. This is absolute potential of point P. Let us suppose to begin with the charge is somewhere here from point R, and you want to move it to point P. Here also you need to do certain amount of work. That work is relative potential. Relative potential at point P with respect to R. In the first case, in case of absolute potential, infinity is the zero potential. Here potential is 0. In case of relative potential, what happens is potential at R is not 0. It is not 0. Here it is 0, here it is not 0. So if you compute potential with respect to zero potential point, then it is absolute. If you consider potential with respect to non-zero finite potential point, then it is relative potential. Changing the reference point amounts to addition or subtraction of a constant to the potential. These are important statements. We better know a little bit deep about them. Potential difference does not depend upon path of integration, but only on the endpoints. See, what he is trying to tell is potential of point, let us absolute potential of point P, it doesn't depend upon the path you have traveled from zero potential point. You can travel like this, you can travel like this, you can come like this, you can come like this, or you can make some 100 rounds and come to the point. Whatever may be the path you followed, you will be getting same value for potential P. So it is independent of path. Without exception, relative potential exists for all charge distributions, finite or infinite. So two potentials, absolute potential, relative potential. Absolute potential exists for most of the charge distributions, first one or two already mentioned, but relative potential exists for all. charge distributions. Now we try to evaluate potential at a point in the field generated by a point charge. See, here is a point charge, capital Q. Surrounding this charge, there exists field. We consider a point here, somewhere here. What is potential here? This is the question. Answer is this one. Q by 4 pi epsilon R, where R is the distance between charge Q, source charge Q to field point P. How this thing has come? For that, what he did is, he considered a point charge Q, located it at the origin. So this is, he located capital Q at the origin. He considered a point P here, somewhere here, at a distance of R. Now, definition. Vp is minus integral infinity to point P E dot dl. E is, what is E here? What is electric field intensity at P, at point P, due to point charge? This thing, you know, it is 1 by 4 pi epsilon Q by R square R cap. Here the expression is in coordinate free form. R, capital R cap, it is in coordinate free form, but we want to perform integration over this expression, so we have to put it in one or other coordinate system. It is very convenient to perform integration when we transform it into spherical coordinate system. In spherical coordinate system, it becomes 1 by 4 pi epsilon Q by R square R cap, small r. Instead of capital R, use small r and R cap. Okay, this expression becomes like this. Q by 4 pi epsilon 1 by R square R cap. This is the expression, of course, for field intensity when Q is at the origin, when Q is over the origin. If Q is somewhere else, expression requires to be modified slightly. We will come to that later. For the time being, here what the point is this. I am interested in potential function due to point charge. For that, I am considering the definition. Vp E dot dl. E requires to be in one or other coordinate system. I am selecting spherical coordinate system, and also I am assuming that Q is over the origin. Then field intensity becomes Q by 4 pi epsilon 1 by R square R cap. This is in spherical system. dl, we decided to be in spherical system, so dl also required to be expressed in spherical system. So this is the expression for dl in spherical system. Now perform dot product, you are left with this. Now perform integration. Ultimately you will be getting like this. So this is potential due to in the field due to a point charge. Right. Now the relation, however, can be extended to configurations in which the source charge is at an arbitrary point. See, to begin with, to make the things simplified, we considered the point charge lying over the origin. He is telling is, even when this charge is somewhere else at an arbitrary point, this relation holds good. General expression is this one. Potential at point P whose position vector R is 1 by 4 pi epsilon charge by distance R cap R prime means location of the source charge. Potential obeys superposition principle, and expressions for single point charge can be extended to other distributions also. In case of group of point charges, you see here a group of point charges are shown. This is a field point. At field point, I want potential due to all these charges. Q1 and P, they are separated by R1, Q2, P are separated by R2, distances, R1, R2, R3, R4, these are distances. Now, potential at P, because superposition is applicable, V is V1 plus V2 plus etc. Bn. But V1 is 1 by 4 pi epsilon Q1 by R1. V2 is Q2 by R2, so on and so forth. So this is somewhat lengthy, you can make it compact by using the symbol sigma. So superposition principle helps us in extending the expression for potential due to a point charge in the field due to several other point charges. Now we can extend superposition principle and expression of potential in the field due to point charge due to continuous charge distributions also. Let us see. Here are three distributions, continuous charge distributions. One is line, another is surface, another is volume. Charge in unit volume is unit length is indicated by lambda. Charge in unit area is indicated by sigma. Charge in unit volume is indicated by rho in these charge distributions. Now we consider small length charge. Small length dl. dl is so small that the charge within this length can be considered as a point charge. It is usually indicated by dq, differential charge. So differential charge over line charge distribution is lambda dl. Similarly, differential charge over surface charge distribution is sigma dA. Differential charge in volume charge distribution is rho d tau. So once we recognize that differential charges in these distributions are point charges, then we can, using the superposition principle, within no time one can find out potentials due to line charge, surface charge and volume charge. It results in V equal to 1 by 4 pi epsilon integral lambda dl by r. Similarly, this is for surface charge, whereas this one is for volume charge. V equal to 1 by 4 pi epsilon integral rho d tau by r. How these are arrived at? See, for continuous charge distributions, this is basic. We have already found potential due to a point charge. Potential in the field due to a point charge. 1 by 4 pi epsilon q by r. Now differentiate it. dV differential potential is dq by r. 1 by 4 pi epsilon. Therefore, V becomes, you have to perform integration, it results 1 by 4 pi epsilon integral dq by r. But dq is lambda dl in case of line charge, sigma dA in case of surface charge, rho d tau in case of volume charge. Therefore, for a line charge distribution, potential becomes 1 by 4 pi epsilon, it is common, integral lambda dl by r. For surface charge, dq has been replaced by sigma dA. For volume charge, as already mentioned, dq has been replaced by rho d tau. So these are expressions for potentials in case of. Now, so far we have considered potential function in the field due to point charge, group of point charges, line charge, surface charge, and also volume charge distributions. All these expressions, they are given here. This is scalar potential functions. For the sake of comparison, field intensities are given in the next column. Notice, one can notice very easily two differences between scalar function, scalar potential and field intensity. One difference is, which is very apparent, which is so obvious, is that field intensity is a vector quantity. R cap is there. Everywhere R cap is there. So it is a vector quantity, whereas potential is scalar quantity. So no vector is there on the right hand side. This is one aspect. Second aspect is field is inversely proportional to distance square, whereas potential is inversely proportional to simply distance. So these two differences are very much apparent, and of course lot of similarity is also there. Similarity is also there. 1 by 4 pi epsilon is there in both the cases. Source charge is present in both the cases. Okay. Now let us move further. In the present slide, which you are seeing, equipotential contours. The concept of equipotential contours are being introduced. In electromagnetic field theory, we come across flux lines. Flux line or field line representation of fields. These are also called force lines. Force lines, field lines, flux lines. These are all concepts, lines, curves used to represent fields. They were introduced by Michael Faraday. Now, another concept, equipotential contours. What are equipotential contours? You see, you consider point charge. Potential is V is 1 by 4 pi epsilon Q by R. It implies Q by R. It implies if you consider some points which are at the same distance from the source charge, R is same. When R is same, field intensity remains same. So, at various points which are at the same distance from the source point, the potential remains same. Those points, if you join all those points, it results in a spherical surface. This spherical surface, over this spherical surface, you can find potential same at all points, here. This surface then is called equipotential surface. Equipotential surface. Equipotential means potential is same at all points over the surface. If you consider a line charge, you can find, we have not done, we consider a line charge, the potential remains same over certain areas. Those areas are called equipotential contours. In fact, the potential is same over cylindrical surface enclosing this particular line charge. So, equipotential contours, equipotential surfaces are, they are surfaces over which the potential remains fixed. In A, here four diagrams are shown. In A, for a point charge, what are equipotential contours? These are equipotential. These spherical surfaces are equipotential surfaces. For large sheet charge, planes parallel to the sheet, they are equipotential contours. In case of straight line charge, as already mentioned, cylindrical surfaces are equipotential. In case of cable also, contours. Cylindrical surfaces are equipotential contours. Now, Apart from equipotential contours, in these diagrams, you can also find flux lines. Flux lines for a comparison to avoid confusion. To avoid confusion between equipotential contours and flux lines are also shown for these charge distributions. How flux lines are drawn? See, let us suppose here this is a point charge. You want to draw flux lines around this particular charge distribution. Then normally what you are supposed to do is place a unit positive charge or positive charge here. According to Coulomb's law, what happens? It simply flies away like this. If you locate your point charge is somewhere here, then it simply flies away because of repulsion. If you keep your charge, it simply flies away like. If you keep it here, it flies away like. If you keep like this, it flies away. It flies away. It flies away. No, these are flux lines. These are field lines. These are flux lines. Basically, they indicate direction of force experienced by a unit positive charge or test charge. Okay, they indicate the force. They indicate direction of force, whereas equipotential contours indicate same potential nature. This is what I want to share now. See you again.